Thank you very much. My name is Victor, and I must say I've seen the horizon. So from Mark's talk, I took the shots yesterday, and now I resurfaced. So nice to see so many of you here, and sorry for not making to your talk, Mark. I did watch it on Zoom, though. Okay, this is work done in collaboration with Elizabeth Winstanley, and it's summarizing several of our results on this topic. This is the rough outline. I'll start with the introduction, then talk about vacuum as well, then rigid rotation, finite temperature field theory, and then show some numerical results, and then conclude. So the motivation slide, we can ask ourselves why it's interesting to study rotating systems. And I will refer to rotation also from the perspective of vortical effects. We have several types of systems where such states exist. For example, we have rotating black holes that we've heard about already today. We have neutron stars where vortical effects can become relevant in relation to anomalous transport. We have quark-gluon plasma where we have some nice experimental results regarding polarization induced by vorticity. And on the other hand, we can ask ourselves why study ADS. We already heard plenty of reasons for this. Let me just summarize. We have the celebrated ADS-CFT duality, so understanding ADS can help us understand conformal field theories better. Then ADS is convenient because it has a time-like boundary, so we have no speed of light surface, as we already heard from Alessandro's talk. If the rotation parameter is really small, I will focus on this regime only today. And because of its maximal symmetry, calculations on ADS are analytically tractable. So we have here a depiction of ADS. Sorry that this picture looks like this. I should have used the AI as well to generate a better one. I will talk about the covering space of ADS, in which the time coordinate goes from -infinity to infinity to avoid closed time-like loops. And I will use this parameterization of the line element that you can see here, where the barred coordinates are coordinates expressed with respect to this L that's related to the Ricci scalar or the cosmological constant through this equation here. In particular, the boundary of the system is located at R over L equals pi by 2. So that's the edge of anti-de Sitter. Let's start with the vacuum propagator. Because of the maximal symmetry of ADS, the vacuum propagator can be written in the form that you can see here as using two scalar functions, curly A, curly B, which depend only on the geodesic interval between the points x and x prime. We also have n slash. This is contraction with the gamma matrices of the tangent to the geodesic. And big lambda is the bispinor of parallel transport that I will show you on the next slide or 2 slides from now. The geodesic interval on ADS can be calculated analytically. It's not our result. It's known for a long time, where we have gamma, the angle between the spatial parts of the two coordinates x and x prime. And A and B, the functions A and B, will satisfy the Dirac equation with the inhomogeneous delta term on the right-hand side. I've just summarized them here. So you can see that, in fact, these equations are not that difficult to solve. So there are differential equations in the geodesic distance. These are the solutions. So both A and B can be written in terms of hypergeometric functions. We are working with finite mass, which is encoded in this parameter K, equal to L times M. L is again the ADS curvature. We have some normalization factor here. Oh, sorry. That's written separately. These are functions of the geodesic distance, and of course the hypergeometric also depends on the geodesic distance. And in the limit that the mass goes to 0, we have these really simple expressions, innocent looking expressions, let's say. And as one can see, BF here diverges when geodesic distance goes to 0. So because of this, one has to do regularization. I will talk about this in the next slide. First, let me stop at the bispinor of parallel transport, which does exactly what it says on the label. It allows spinors to be parallel transported from one point to another. So it depends on 2 points, x and x primed. And because of the maximal symmetry, again, it satisfies a differential equation that looks like this. So we have a covariant derivative where we have an index, space-time index, And on the right-hand side, we have spin part and the tangent to the geodesic, and again, the geodesic distance. Because it's related to the spin structure of the spinners, of course, lambda will depend on how what kind of tetrad we're using for the spinner. And in particular, we use this Cartesian-like tetrad, where the I hat is a spatial index and xi, xj are defined as just as in normal spherical coordinates with respect to theta and phi and the radius. And with this choice of tetrad, lambda looks as you can see here. So again, it's not so evil as it may seem. Okay, let's move on to regularization. So for regularization, we are, of course, interested in evaluating some expectation values in the vacuum state of various observables. And the observable which is of interest is the stress energy tensor, which can be written in this form. Eventually, it involves, sorry that I put alpha and beta and not A and B as before. They are the same functions, of course. So the stress energy tensor involves only the function B and its derivative. Because of maximal symmetry, T mu nu will be proportional to the metric, the space-time metric. And in the end, if we apply the Schwinger-DeWitt prescription, this is the result. Without skipping some details, of course, this is the result, which agrees with the Pauli-Villar regularization reported previously in some work by Campores in Higuchi. We may ask ourselves, how dependent is this on the regularization scheme? And in order to find out, we have to switch to a different regularization scheme. And the most convenient one is the Hadamard regularization, for which we have an expression for the singular part of the two-point function. This singular part is written for an auxiliary function, curly G, which is related to the Feynman propagator for the Dirac field via this equation. So in the end, applying the Dirac equation on the Feynman propagator will show that GF satisfies a Klein-Gordon-like equation, but of course, GF is still a bispinner. The functions appearing here that are related to the singular part of propagator can be obtained in closed form. And here they are, again, a hypergeometric. And subtracting this singular part, we end up with a renormalized energy momentum tensor, which looks like this. And this is not the same as this. Thank you. Because there are some different coefficients for the k-squared terms, the k-squared and k to the fourth terms. Okay, this is the vacuum part. Now let me move on to rotation. So in order to study rotation, first let's understand what properties we can expect for rotating systems. In an arbitrary spacetime which has spherical symmetry, one can employ this kind of parameterization of the line element, where the functions W, U, V are equal to 1 for Minkowski, and for ADS they are simply given by these expressions. And from a classical perspective, we can study the properties of rigidly rotating state as a global equilibrium state. And it's not difficult to see that the velocity of a fluid which is rigidly rotating looks like this. This is related to the Killing vector giving rotation. And the temperature of the state is related to a constant value T0 multiplied by the Lorentz factor gamma associated to an observer which is co-rotating with this rotation. Okay, so this is something we will find also on ADS. Properties of rotating systems, for example, in Minkowski space, have been studied for a long time. And we have this really nice effect which emerges once we calculate expectation values called the axial vortical effect. The axial vortical effect says that if we put a bath of fermions in rotation, then this will generate an axial current which is parallel to the axis of rotation. In short, we have this relation between the axial current and the vorticity, where sigma is conductivity. It's the chiral vortical conductivity. This is a function of the temperature, also of the vorticity, acceleration. Temperature also depends on vorticity because it's a function of position in space-time. And we can continue this as a series in the mass of the field. So the question is, what happens on anti-de Sitter? And on anti-de Sitter, again, we have to talk about vorticity and all these kinematic vectors. This is a schematic representation of what they look like on anti-de Sitter. What we will uncover is the fact that due to non-vanishing curvature, there is an extra term in this conductivity, which is related to the Ricci scalar. Okay, how do we calculate the expectation values at finite temperature? We have to use point splitting approach, or this is a convenient way to do it. And thermal states are defined with respect to a density operator given here. We have a Boltzmann factor, beta 0 times Hamiltonian. And in order to encode rotation or to put angular momentum into the system, we have to introduce this coupling between a constant rotation parameter and the angular momentum of the system. So, for example, the expectation value of the axial current is psi bar gamma 5 psi, or psi bar psi is replaced by the Feynman propagator, and bispinor of parallel transport to allow the coincidence limit to be taken along the geodesic. In order to find the Feynman propagator at finite temperature, we have to do some work, and this work essentially boils down to finding the KMS relation or KMS condition, which is satisfied at finite temperature by the Whiteman functions. Here are the KMS relations. In principle, to derive them, we can take into account the action of the density operator on the field itself. And the action is, as you can see here, it shifts the time coordinate with an imaginary quantity, also shifts the angular coordinate with an imaginary quantity. And we have here a spin part related to this rotation. So in the end, we can write the Feynman propagator at finite temperature as an infinite sum or image sum over the image sum of the vacuum propagator over these points shifted according to the KMS relation. Okay, so I'll skip the calculational details. Just with plugging everything into this formalism eventually gives a formula for the conductivity, which is written here in full generality. This is completely non-linear, so it takes into account all the curvature terms and so on. And if we try to do a large temperature expansion, then this is what comes out. We have the curvature correction as advertised before. It's not in the t-squared part, of course, because of it's not permitted by the units. And it appears only in the large temperature limit. So in order to see it, we have to go at high temperatures and then sort of compare this prediction with a numerical evaluation of the sum appearing here. One particular feature is that if we set the rotation to be critical, so the maximum rotation supported by the space-time before we have a speed of light surface, then miraculously in the equatorial plane, everything becomes constant. So it's like the critical rotation is balancing the clumping tendency of anti-de Sitter, and even the axial vertical conductivity becomes a constant, and it's again given by this hypergeometric function. So just to show you some plots, we have a representation of the axial vertical conductivity normalized. Oops. So let's square this. So we have dimensionless result on the y-axis. And here we have the distance from the ADS center. Everything is taken in the equatorial plane. Theta is equal to pi by 2. Here we have massless fermions. K is equal to 0. And we see that if we have critical rotation, then we get these straight lines at two different values of the temperature. And if we look at smaller values of the rotation, then we get this kind of behavior. So everything goes to 0 as we approach the boundary of ADS. Here are results for various values of the mass. So K equals 0 and K equals 2. And again, the dashed lines are the expression, the analytical asymptotic expressions, and the colored lines with symbols are direct evaluations of the sums. Okay, here we can look at dependence with respect to temperature, basically, of again, the vertical conductivity. And we find that it's a really good agreement with the analytical formula. In order to see that we are not fooling ourselves, because t-squared dominates, of course, over the finite over the temperature independent term, we can take away from the numerical value of the conductivity, we can take away the analytical asymptotic prediction, and we see that in the large temperature limit, this will go to 0. So we are indeed capturing the high temperature behavior by just the asymptotic formula I showed you. Another interesting thing, which I will tell you about before ending, is what happens to the axial flux. So the axial flux is basically the axial current integrated over hypersurface in ADS. And what we can predict about this axial flux is that because of this conservation equation, we see that the axial flux is not conserved if the field is massive. What sits on the right-hand side is the pseudo-scalar condensate, which is simply psi bar gamma 5 psi, and with a factor of I here. And in the end, calculating the axial flux as this kind of integral, so we have a radial integral and integral over the angles. We find a very interesting behavior that for massless fermions, because the axial current is conserved, we have a constant value of the axial flux throughout the whole space-time. So z bar is just some vertical distance going to infinity as we approach sort of infinite distance from the horizontal plane. So it means that these chiral fermions will escape through the ADS boundary at infinity. If instead we turn on the mass, then because of the conservation equation related with the pseudo-scalar condensate, the axial flux will die and eventually will go to 0 as we approach the ADS boundary. So we can say that the ADS boundary is transparent to massless fermions, but it's opaque if the fermions are massive. Okay, these are some analytical expressions, but I will skip this and go directly to the conclusion and remind you that the KMS relations allows us to write the thermal two-point function in terms of the vacuum 1. And because of the maximal symmetry of ADS, the vacuum 1 can be found in closed form. With the help of these functions, we were able to uncover the axial vortical effect on ADS and to calculate the curvature-related correction. And also, we are able to compute the axial flux and to show that for massless fermions, this comes from the southern hemisphere and goes through the northern hemisphere. While for massive particles, there is no flux at the boundaries. Okay, thank you very much.
Thank you very much. We have time for a couple of quick questions.
Thanks for the nice talk. I just have a very, well, out of curiosity. In the beginning, you said that for the renormalized stress tensor, only the function B enters and not A. Is there any simple reason why, or is it just an accident?
No, it's not an accident. It's the gamma structure. So we have here a trace over spinor indices, and we have a gamma function appearing here, and the trace vanishes for any product, any odd product of gamma functions, of gamma matrices. Sorry.
And the spinor parallel propagator only has even powers of gamma.
Yeah.
Okay.